this lecture, we are going to study about memory allocation. So we know that we have our main memory, and then the operating system and the user processes have to be loaded into the main memory for execution. Now, talking about main memory, we have also discussed about a few problems, like how do we protect the operating system from being accessed by user processes, and also how do we prevent user processes from accessing each other. So in order to solve these problems, we have made use of something known as the base register and the limit register, using which we specify a memory space for each of the processes, and we do not allow any processes to execute or access anything beyond its own memory space. So this was made possible using the base registers and the limit registers, and also in dynamic relocation, we saw that we made use of something known as a relocation register, which holds the lowest physical address, and we also saw the memory management unit, which helps in converting logical addresses to physical addresses. So these were some of the problems that we have already discussed, and we have found the solutions. So now in this lecture, we want to mainly focus on how to allocate memory. So we know that we are having different processes. Now how will these processes be allocated the memory? We have a certain amount of main memory, and we cannot simply give the complete main memory to one single process. We have to allocate this memory to different processes. So the question that we are going to discuss in this lecture is how to allocate memory. So let us see how memory is allocated. So here, in the simplest form, what we are going to do is we will divide the memory into several fixed size partitions. So we have our main memory, and this main memory will be divided into several fixed size partitions. And then what happens? Each partition may contain exactly one process. So the partition that we made here in step 1, we need to make sure that in one partition only one process can reside. So there cannot be more than one process residing in one partition. And then when a partition is free, a process is selected from the input queue and is loaded into the free partition. So we know that the processes that are ready to be executed, they wait in the ready queue or the input queue as we call here, and whenever there is a free partition from among these fixed size partitions that we have formed, so a process will be selected from the input queue and it will be loaded into one of the free partitions that we have. Then when the process terminates, the partition becomes available for another process. So once a process completes its execution, the process will terminate, and what will happen? That process will be taken out from that particular partition that was assigned to it, and hence that partition will become free and it will be available for another process. So this is one of the simplest methods for allocating memory. So this is how memory is allocated in the most simple way. Alright, so let us go into a little more detail of this and see how this works. So here we have the main memory. So think of this rectangle that is shown here as the complete main memory that we have. Now what is this thing that we have to do? We have just seen that this main memory is divided into several fixed sized partitions. So here let us say that these are the partitions into which we divide our main memory. So the memory is divided into several fixed size partitions. So this is the partitions that we have. Now what happens? Let us say that we are having these processes that are waiting in the ready queue. So these circles over here, I am using them to represent the processes. So now if you see the circles, you see that all of these circles are of different sizes. Now I am representing it in this way in order to show that the different processes, they will have a different memory requirement. So let's say that there is a process here, and depending upon the size of this process, it is going to need some amount of memory. Now if you see this process here, it is bigger than this process. So it signifies that this process right here is having a bigger memory requirement than this. And similarly for the others. So if you see, this is the smallest process, so it will need the smallest amount of memory, and this is the biggest process here, which will require the biggest amount of memory. So now the task is, we need to pick these processes from the input queue, and we need to allocate them the fixed partitions that we have in our memory. So what we have to make sure is that the partition that is assigned, it is big enough to hold that process. So for example, let's say that we are taking this process. So let us see in which of these partitions can this particular process fit into. So if you see here, this process can easily fit into the first partition that we have. So just take into account the size of the rectangle and the size of the circle. I am using this purely for representation purpose. So I hope you will be able to understand it. Okay, so this process is able to fit here. So we can allocate this particular partition for this process. And also if you look here, the same process can also fit in this particular partition over here. So it can also be allocated this particular partition. And if you see here, it is not going to fit into the third partition. You see that the third partition, it is small and this process is not fitting. So we cannot allocate this. Now, what about the fourth, fifth and sixth one? Yes, this process can easily fit into the fourth, also the fifth and also the sixth. So we see that this particular process that we have, it can fit into any of these fixed size partitions except the third one, which was too small for this. So like this, depending upon the size of the process, which represents the size of memory that it needs, they will be allocated a certain partition in which they can be loaded and they can do their execution. Alright, now let us see another scenario. So here I am taking another example here, and here we are having some more partitions. So this is our main memory, and here there are 1, 2, 3, 4, 5, 6, 7 partitions of different sizes, and these are the processes that are waiting in the ready queue or in the input queue to be executed. So now let us see how we can pick these processes from the queue and how can we allocate them the different partitions of memory. Now if you see, we have this process and all of the partitions are empty at the moment. So we can easily put this process into the first partition. Alright, because anyway it is going to fit here. Now coming to the next process, if you see this process, this is big and it will not fit into the second, third, fourth or fifth. So where will it fit? It can fit into the sixth partition over here because of its size. Now this will be allocated this memory location because it is having a bigger requirement of memory. Alright, now coming to the third process that we have. This is the smallest process, and if we start scanning from the topmost free partition, we see that this partition is free and this will definitely fit into this partition. So this can be easily allocated, this partition over here. And then what about this process here? We see that this process is not going to fit here, nor here, nor here, but it will be able to fit in this partition over here. So we can allocate this partition for that process. And now we have this big process that is waiting, and if you see, there are no partition in which we can accommodate this process. So we see that we are having some free partitions, which is 1, 2, 3. All these 3 are free, but they cannot accommodate this particular process. This partition is too small for this process, and also this is also small, and this is also small for this process. So in this kind of a scenario, what can be done? So if we think of it logically, one thing that we can do is we can combine these 3 partitions into one big partition, and then we will be able to accommodate this process into this partition over here. So that is one thing that we can do. So this is something that is done in memory allocation. But keep in mind a very important thing, that this kind of merging of different partitions into one can be done only when the partitions are contiguous. That means when they are consecutive to each other, they must be adjacent to each other. So here we see that these 3, they are consecutive or they are adjacent to each other. So it is possible to merge them into one. So for example, let's say that there is one free partition here, and then there is another somewhere here, and then there is another somewhere here, and in between there are occupied partitions. So in that kind of scenario, we will not be able to combine them and make them one. They can be combined only when they are contiguous. So here it is possible, they are adjacent to each other and they are all free. So we can combine them into one partition like this. And if we combine them into one partition like this, this process can easily fit into this partition now. So this is how memory allocation is done. If there is a process that is too big and it cannot be accommodated into any of the partitions, we can search if there are any contiguous free partitions and we can combine them into one, and we can try to accommodate that particular process. Alright, now let me take one more scenario. So let's say that this is our case now. So here we are having our main memory, and this first, second, fourth and fifth partitions are already filled, and we are having one big partition which is free over here, and then there are two processes that are waiting in the input queue. So now what can we do? There are two things that we can do. The first thing is I can either let one of these processes take this complete big partition and let the other one wait. So for example, I can allow this process to make use of this memory location and it can execute here, and at the same time this one will be waiting. Or I can do the same with this. I can allow this one to execute and allow this one to wait. But if you look carefully, you see that this memory location is big enough to hold both of them. But we already said in the beginning of the lecture that in a single partition, only a single process can be allowed. We cannot allow more than one process in a single partition. So what can we do in this scenario? We can do the opposite of what we did in the previous case. So in the previous case, we merged the free partitions into one. Now in this case, what we can do is we can repartition this one big partition into two. So what we can do here, I can split this big partition into two smaller partitions like this. Now if you see, both of these processes will be able to execute. I can allow both of them to execute. I can let this one be accommodated here, and I can let this process to be loaded in this portion of memory. So both of them can be accommodated and both of them will be executed. So this is how in most cases the memory allocation is done. So we have seen how our main memory is divided into several fixed size partitions, and we have also seen that only one process can be allowed in one particular partition, and then we have also seen how we can accommodate different processes into the free partitions that we have, and we have also seen how we can merge the contiguous partitions into one in order to accommodate bigger processes, and we also saw here how we can split some big partitions into multiple partitions in order to accommodate smaller processes. So these are the main important things that you need to keep in mind about memory allocation. Now also there are a few more things that we need to know about, as in the case of which partition should be assigned to different processes so as to maximize our storage utilization and efficiency and speed. So that topic we will be discussing in the next lecture. So I hope this lecture of memory allocation was clear to you. Thank you for watching and see you in the next one. In this lecture, we'll be discussing about dynamic storage allocation problem. So in the previous lecture, we have seen how memory allocation is done, and I told you that there are a few things that we need to keep in mind while allocating the particular free partitions to the processes. So that is what we are going to discuss here, the dynamic storage allocation problem. Now what is this problem? So the problem is how to satisfy a request of size n from a list of free partitions or holes in the main memory. So we are having a request of size n. That means we are having a process which is having a size of n, and that size of n represents the amount of memory that the process is going to need for its execution. So for such a process, which is the partition or hole that we are going to assign from the main memory? So when we say hole or partition, it just means the fixed partition that we were having in the main memory that we discussed in the previous lecture. So the question is, which is the partition that we are going to assign for a particular process which has a particular amount of memory requirement? So as a solution to this problem, we are having three approaches. So the first one is called first fit, the second one is called best fit, and the third one is called worst fit. So we will be seeing these solutions or approaches one by one, and we will try to understand what it means and how are memory partitions allocated to different processes in these three different approaches. Alright, so let's start with the first one. So the first one is first fit approach. So what happens in this first fit approach? So in this first fit, we allocate the first hole that is big enough. That means we will be just picking up a process from the input queue, and we will be seeing which is the first partition that we have which can accommodate this particular process. So we'll be just starting from the top of the main memory, and we will see the first partition that is big enough to hold this particular process. And then searching can start either at the beginning of the set of holes or where the previous first fit search ended. So when we are scanning for the holes or the partition, the scanning or the searching can start either at the beginning of the set, that means from the top of the main memory, and we can go down, or we can start at the place where the previous first fit search ended. So I will be explaining this further when we explain it with a diagram. So let us see what is the next point. We can stop searching as soon as we find a free hole that is large enough. So as I said, when we see that we find a partition that is big enough to hold that particular process, we just end the search and we assign that particular partition to the process. Alright, so let us just explain this using a diagram. So here I'm taking that same diagram from the previous lecture that we have taken. So here we have the main memory. It is divided into several partitions. So we have 1, 2, 3, 4, 5, 6 partitions, and we have 1, 2, 3, 4, 5 processes that are waiting in the ready queue or in the input queue. So in this first fit approach, what we are going to do is we are going to take a particular process and we are going to just start searching for the partitions from top to bottom, and we are going to see if this particular process can fit into any of the partition. So the first partition that we find which is large enough to accommodate this process will be the partition that will be assigned to this particular process. So for example, if we take this process and if we start scanning for the partitions from top, we see that we have this block of memory or this partition which can very well accommodate this process. So what will happen? This process will be allocated this particular partition over here. Okay, now coming to the second one. Now this process, now let us see where can this process fit. So we see that if you try to fit it here, it is not going to fit from the size. You can see that this memory location is smaller than this process, and also if you look at the third one, it is smaller than the process, so it is not going to be able to fit here. Okay, now what about here? So here we see that this is big enough to hold this process, so we can easily accommodate this process in this partition over here. Now coming to this third process. Now for this third process, before we allocate any partition, let us read the second point again. So here it says, searching can start either at the beginning of the set of holes or where the previous first fit search ended. So when we are going to search for a partition for this particular process, we can either start searching from the top, that means from the beginning of the set. Now where is the beginning of the set? The beginning is here. This one is already occupied. Now this is the beginning. We can either start searching from here, or we can start from the place where the previous first fit search ended. Now which is the place where the previous first fit search ended? It is here. So for the previous process, when we were searching for a partition, this was the partition that was found and this was the partition that it was allocated. So this was the place where the previous first fit search ended. So we can also start searching from here. So it is up to us. So let's say that we are going to start from the beginning of the set. So we are starting from the beginning here again. Now if we start from the beginning, this is occupied, this is the next free one that we have. Can this process be accommodated in this free one? Yes, definitely it can be. So we accommodate this process into this partition over here. Now let's see, let us take the fourth one. So the fourth one, if you check, it is not going to fit here. And what about here? Yes, it is going to fit in this location. So we can allocate this memory location for the fourth process. Now we see that we have the fifth process that is waiting here, and this fifth process cannot be allocated to any of the free partitions at the moment. Why? Because it is not going to fit. It is not going to fit here, nor is it going to fit over here. And we are not able to combine these two free partitions also. Why? Because I already told you in the previous lecture, we are able to combine them only if they are contiguous. So here they are not contiguous, they are not adjacent to each other, so we cannot simply combine these two memory partitions. So this process is going to have to wait in this ready queue until and unless this particular process maybe finishes its execution, because this is the only partition where it can fit. So this is what happens in the first fit approach when we try to allocate memory partitions to processes using the first fit approach. Alright, now let's go to the second one, which is best fit approach. Now in this best fit approach, let's see what happens. We allocate the smallest hole that is big enough. So in this best fit approach, we will be picking up a process and we will be allocating the memory location to that process, which is the smallest memory location, but it is big enough to hold that particular process. So we follow this in order to not waste the memory that we have. So here we must search the entire list unless the list is ordered by size. So in the previous one we saw that we were just scanning from top to bottom, and whichever we found is fitting, we just put it there. But in this one, we need to search the entire list from top to bottom unless the list is already sorted by size. So we have to search it from top to bottom and we have to find out which is the best fit for a particular process. So this strategy produces the smallest leftover hole. Okay, so let us take the diagram and try to explain this again. So here we take the same diagram, the same example that we took in the previous case. We are having this main memory with these partitions and these processes waiting in ready queue. So now let us pick up the first process and see. So we pick up this first process and we scan the entire list. That means this entire main memory we have to scan to find the partition that is the smallest one that can hold this particular process. So if you see here, this process can definitely fit in this, but this is not the smallest one. So what about this? Yes, this process can fit even into this partition here. And also if you see this, it is not going to be able to fit in this third partition. And what about this? It is going to fit here for sure, but this is too big. And also for these last two partitions, they are definitely going to be able to hold this process, but we see that the smallest partition which can hold this process is this second partition over here. So we will allocate this process to this second partition over here, which is the best fit for this particular process. Alright, now let's come to the second process. Now for the second process also, if we see in the similar way, we can find that this partition over here, this is the smallest one which can accommodate this particular process. So we will allocate this memory location to this process over here so that it fits somehow perfectly into this. And now what about this third process? From the diagram it is very easy. We can see that this process can easily fit into this smallest partition, which is this one. So it is allocated this partition here. And what about this one? It can easily fit into the smallest partition which is available, which is this partition over here, which can easily accommodate that. So this partition is assigned for that process, and we have this remaining big process, and this big process can be easily accommodated in this big partition that we have over here. So it is also accommodated here, and we see that all the processes which were waiting in the ready queue are given some partition or the other, and we see that they are perfectly, or at least they are close to perfect in fitting to these memory partitions that we have. And there is only one partition that is left empty. This is the only free partition or the hole that we have. So it says here the strategy produces the smallest leftover hole. So this is what happens in the best fit approach. Alright, so we see that we are actually minimizing the wastage of memory if we are using this best fit approach. Alright, now let us go to the last approach. So the last approach that we have is the worst fit approach. Now what happens here? In worst fit, we allocate the largest hole. So from the name itself, it says it is the worst fit. So what we are going to do, we will just take the process and we will see which is the biggest partition that we have, which is free. And then we will just be allocating that process to that biggest free partition. So we must search the entire list unless it is sorted by size. So just like the previous case, here also we have to search the entire list unless the list is sorted by size in order to find out which is the largest partition or the largest hole that we have. And this strategy produces the largest leftover hole. Okay, so let's explain this also using the same example, using the same diagram. So yes, we have the same example over here again with our main memory and partitions and the processors waiting in ready queue. So let's take the first process here. We take this process, and what do we have to do? We have to allocate it to the largest hole. Now, which is the largest hole in our partitions? It is this one. So we will take this process and we will allocate it to this largest partition over here. Okay, now what is the next one? This is the next process that we have. So which is the largest hole that we have now? This is already occupied. So the next largest hole that we have is this one right here. So we will put this process into this hole now. Okay, now what is the next one? The next is this process here. And what is the largest hole that we have? So this looks like the largest hole. We will put this process into this hole over here. And also for this process, what is the largest hole that is available now? This is the largest hole that is available. We put it there. And what about this process? We are not able to allocate a memory location to this process now because there are no free holes that is big enough to hold this particular process. So it will have to wait until some or the other processes freeze their memory location and it may get a chance to execute. Okay, so this is what happens in the worst fit. So from this illustration itself, you must have got an idea that best fit and first fit, they are definitely better than the worst fit that we have discussed in terms of storage utilization. But if we are trying to compare best fit and first fit, it has shown in simulations that in some cases best fit is better, while in some cases first fit is better. So we cannot say for sure which is better, first fit or best fit in case of storage utilization, because it depends upon system to system and also there are many other factors that affect it. But in case of speed, first fit is faster than best fit. And why is that? From what we explained, I hope you already have understood that, because we are just allocating the first available partition that is large enough to accommodate that particular process. So it is faster. Alright, so these are the three approaches that we have for allocating memory partitions to particular processes. So I hope this lecture was clear to you. Thank you for watching and see you in the next one. In this lecture, we are going to discuss about fragmentation. So let us see what is this fragmentation. So as processes are loaded and removed from memory, the free memory space is broken into little pieces, which results in fragmentation. So in the previous lecture, we have seen how memory is allocated and we have seen the different approaches we follow for memory allocation. Now what happens is, when these processes are loaded and then when they are removed from memory, there will be free partitions that are left in between these memory partitions that we have. And these partitions, they become like small broken little pieces of memory, which results in fragmentation. So what do we mean by fragmentation? They are the broken pieces of memory. That means they are the free memory partitions that are left in between, and they cannot be even combined into one chunk of memory in order to accommodate some bigger process, but they are just left as free spaces in between, and that is what we call fragmentation. Alright, and also there are two kinds of fragmentation that we have. So first one is external fragmentation, and the second one is called internal fragmentation. So we will see what are these two types of fragmentation, how do they differ from each other, and is there any way we can prevent these fragmentations from occurring, or if there is any way to recover from this fragmentation. Alright, so let's go to the first one, which is external fragmentation. So in external fragmentation, let's see what happens. It exists when there is enough total memory space to satisfy a request, but the available space are not contiguous. So this external fragmentation occurs when we are having free spaces in memory, but they are not contiguous. So if you add all the free spaces that are present as blocks here and there, they together form a big block, but since they are not contiguous, we are not able to merge them together, and hence we are not able to satisfy the need of the processes. So this is when external fragmentation occurs. So the storage is fragmented into large number of small holes. So we will see this when we take the diagram and explain it. And this fragmentation problem can be severe. In the worst case, we could have a block of free or wasted memory between every two processes. So between every two processes, if there is a block of memory that is free, then we see that that particular memory may be too small for accommodating a particular process later on. Also, they are not able to be combined into one single memory block because they are not contiguous. So in the worst case, if we are having a block of free memory between every two processes, then that could be a severe problem. So if all the small pieces of memory were in one big free block instead, we might be able to run several more processes. So this is what I just explained. So let's take the diagram and try to understand. So here I am taking a diagram where this is the main memory, and these are the different partitions or blocks or holes that we have. And let's say that all of the blocks or all of these holes are right now occupied by some or the other processes. So we see that all of them are occupied, and still there are two processes that are waiting in the ready queue. Okay, so at this moment we are not able to satisfy the request of these two processes because everything is full. Now let's say that at some point of time, some of the processes finishes their execution and they leave. So let's say that the process which was in the second block, in the fourth block, and in the sixth block have left. So these memory locations or these blocks now become free. But are we able to accommodate these processes into these blocks? So if you look at the size, you can see that this process is too big to be accommodated here, and it also cannot be accommodated here nor here. And even this bigger process here, it cannot be accommodated in this, nor this, or this. So we see that these three blocks, these are the unusable external fragments at the current moment. So why do I call it the current moment? That is because we are having these two processes that are waiting. If there is a smaller process which can be accommodated in any one of these, we can very well take it and we can allocate that process here. But at the current moment, we see that these two processes cannot be accommodated in any of these, and hence this is the unusable external fragments at the moment. But if we were able to combine these three segments into one, then we could accommodate at least one of these processes. But we are not able to combine. Why? Because they are not contiguous. So when we studied about memory location, I have already said that we are able to combine or merge segments only if they are contiguous. So in this case, we cannot do that. And this is what we mean by external fragmentation. Okay, so now let's go to the next one, which is internal fragmentation. So let's see what happens in internal fragmentation. So in internal fragmentation, it occurs when memory blocks assigned to processes are bigger than what the process actually needs. So here, from the name internal itself, we can try to understand that this is the fragmentation that occurs internal or within the block itself. So within the partition or within the hole itself, if there is a fragmentation occurring, that is what we call internal fragmentation. And when does this occur? This occurs when the memory block that are assigned to the process are actually bigger than what the process actually needs. So if we are assigning a big block to a process that actually does not need that big block, then what happens? That process will be using that block, and we know that only one process can be loaded into one particular block, and hence this process since it does not need that complete block, still it is holding that and it is using only some portion of that block, and the remaining part is wasted. It is not being used. So that is when internal fragmentation occurs. So some portion of memory is left unused as it cannot be used by another process. So that is what I just explained now. So let us take this diagram again and try to understand this. So here, let's say that this is again our main memory and these are the partitions we have, and these are the processes that are being accommodated in these partitions. So if you see here, for this particular process here, it is not a very big process, but it is assigned this big memory block. So it is not even making use of this complete segment. It is using only this much area of the memory, and this remaining area of memory is left unused. So it is wasted. So similarly for this process also, this memory location is actually too big for this process. So the remaining portion of memory is not used. Similarly for this process as well. So we see that these are the memory locations that are unusable. They are the unusable internal fragments at the current moment. So as we said in the point over here, some portion of memory is left unused. So this is the one that is highlighted here, and it cannot be used by other processes. Why? Because only one process can be accommodated in a memory block at a time. So here we see that the fragmentation is occurring internally within the block or within the segment of memory itself. So that is what we mean by internal fragmentation. Now, do we have a solution for this? Let's see. So the solution is make use of best fit approach for allocating memory segments to the processes. So in the previous lecture, we have discussed about first fit, best fit and worst fit approaches. So if you are making use of the best fit approach, we see that we were allocating the processes to the memory location that is the smallest memory location that is just big enough to hold that particular process. So if we do that, we will actually not waste our memory. We will be allocating memory to processes in a very economic way, and hence we will not be wasting any of the memory, and hence by following this best fit approach we will be able to prevent internal fragmentation at least up to some extent. Okay, so that is the solution to internal fragmentation. But what about external fragmentation? We have discussed about the problem, but we didn't discuss any solution to that. So let us see now if there is any solution to external fragmentation as well. So coming to the solution to external fragmentation, we have a solution which is called compaction. So compaction is a solution to the external fragmentation. So let us see what do we mean by this compaction. So compaction means shuffle the memory contents so as to place all free memory together in one large block. So in the previous example that we took for external fragmentation, we saw that there are free memory locations in between the other blocks, and they were not usable because they are not contiguous. And we know that if they are contiguous, we are able to merge them into one and we can make use of them. So in this compaction, what we'll do is we'll shuffle those memory locations or those blocks so that the free ones all come together as one single block, and we can merge them and we can make use of them. So let's take this example again. So this was the same example that we took for external fragmentation, and we saw that these three highlighted blocks were the unusable external fragments at the current moment. Now, what if we combine these three? We know that we cannot directly combine because they are not contiguous. So the first thing is we have to make them contiguous. So for that, what we'll do, we'll shuffle it so as to place all the free memory together. So let's say that we are shuffling it and it forms a pattern like this now. So all the occupied ones are on top and all those unoccupied memory locations or those blocks are put together over here like this. Now what we can do, we can actually combine these three. We can merge them together. So let's merge them, and after merging, what happens? This becomes a usable block of memory now. So now I can either allow this process to execute or this process to execute. They can be allocated this memory location. But here, let's see if we can become even more efficient. We see that this block is actually large enough to accommodate both of them. But we know that in one block, only one can be accommodated. So in the first lecture, when we discussed about memory allocation, I already told you that there is a process where a big block of memory can also be split into multiple blocks. So what if we split this big block into multiple blocks? So let us split it. Now if we split, we see that we can accommodate both these processes. So this first process I can put it here, and the second process I can put it here. So you see both of them will be able to get the memory blocks and they can do their execution. So this is one solution that we have for external fragmentation. But this also has some problems associated with it. So let's see what they are. So the problems are, number one, compaction is not always possible. So we may think that, okay, whenever external fragmentation is there, we can just shuffle it and we can bring all the free blocks together and merge them and we can make use of them. But this is not always possible. And why is that? If relocation is static and is done at assembly or load time, compaction cannot be done. So we have already talked about this relocation being static and if it is being done at assembly time or load time and all that in the previous lectures. So if the relocation is static and is done at assembly or load time, then the compaction cannot be done. So compaction can be done, or it is possible only if relocation is dynamic and it is done at execution time. So only if relocation is done at execution time, compaction is possible. So in the other cases, compaction will not be possible. So we see that we have a solution to external fragmentation using compaction, but this is not the best solution because this cannot be always used. Okay, so that was about fragmentation, external fragmentation and internal fragmentation, and the possible solutions that we can have to solve these fragmentations. So I hope this lecture about fragmentation was clear to you. Thank you for watching and see you in the next one.